Hey. Hope everybody had a good first day. Let's see, we should get this up and running. Okay, awesome. So, I think at this point it's becoming almost a joke. I think most of you have probably seen maybe one of my whiteboard videos on YouTube, so I thought we'd do something a little bit different and actually do the keynote as a whiteboard video as well. So today I wanted to spend a little bit of time talking about sort of zero trust security, right? I think it's a pretty broad topic. Obviously, I joke if you ask 5 people what is zero trust, you're going to get 6 different answers. So I wanted to maybe spend a little bit of time unpacking, what is zero trust, how do we think about it, how do we define it, and then dig a little bit more into how we think about actually solving for zero trust. So that's a whole bunch of topics. We're going to do this in a bit of a lightning round. And if I make any mistakes along the way, you'll forgive me. We're going to do sort of a real-time whiteboard here. So maybe zooming out, I think safe to say probably most of you at least know HashiCorp. But sort of setting the top-level story, I think for us our focus has always been how do we support development teams in their mission to deliver applications. Right? I think for almost every business, that's really the core business value, right? That's what really drives new users, new features, new revenue, right? That's ultimately what we care about. Unfortunately, better or worse, we haven't figured out a way to make the applications run in thin air. So there's an infrastructure underneath that is supported by our operations and our platform teams, right, and security. And so these operations and platform teams are responsible for delivering that infrastructure that the applications run on top of, right? Now, I think if we go back, many years, life was easy. Everything was a private data center running VMware or OpenStack, so we only had one environment that we had to think about, one environment that we had to build our process around. But our world doesn't look like that anymore, right? Now we're running private data center. We might have Amazon, Azure, Google, GCP. If we're in China, we'll have Ali Cloud. And I think for a lot of organizations, now thinking about edge, right? So if you're a retail store, you might say all of my 1,000 stores are an edge location, or my manufacturing plants are edge. Or in some of the cases, each of my vehicles might be an edge. So I think we're seeing this sort of explosion of compute infrastructure now running everywhere. And the challenge is these are all very inconsistent environments, right? The way I might deploy and manage an app on Amazon, very different than the way I'm going to do it on Azure or Google or, in an edge environment. So it's really across all of that's where we think about the role of HashiCorp, right? And so we think about our place as how do we make this problem a little bit easier, right? On the left side, or the right side I should say, we think about how do we make this a consistent process. Oops. And the example I would use here is Terraform, right? With Terraform, you could build a single pipeline for how do we define infrastructure as code, connect that to our version control system, and then have one process for how I author code, test it, and then ultimately go out to production. But it doesn't matter if that's running in Amazon or Azure or Google. It's the same pipeline. There's a consistent workflow, right? On the other side is thinking about what's the relationship between our development teams, our application teams, and our operations teams. And I think historically this relationship here was a ticket, right? If I want to get some VM infrastructure, I file a ticket and I wait a few weeks and someone provisions it for me. If I want to update a firewall, I file a ticket, someone manually updates the firewall. If I want a certificate, file a ticket with security, someone makes a certificate for me. So how do we move to a self-service view where our development teams are free to deploy as often as they want, provision infrastructure, manage the life cycle of their applications without filing a ticket? And so that's really a shift away from a ticket-driven approach to more of an API-driven or UI-driven or GitOps-driven workflow, right? So that's how we think about the very big picture of what we're trying to get to. Self-service for our development team so they can go as fast as they want, ultimately to deliver those applications, but then doing it in a way that's consistent across a multi-cloud environment. That's a very big problem space, as you can imagine. So if I sort of double-click into it, there's a whole bunch of different layers that we focus on, right? At the base, we think about provisioning and what is the life cycle of our infrastructure. And so when we talk about provisioning, probably the first thing that comes to your mind is Terraform, right? And that's probably our flagship product in the provisioning category. But I'd also put our Packer tool here as well, right? I joke if Terraform is Batman, Packer is Robin. They sort of are designed to work together. And so Packer is very much sort of a part of that infrastructure as code lifecycle, right? So today I want to spend most of the time focused on security, so I won't go in detail on those two. At the next layer up, is thinking about what are the security challenges. And here's where I'd put our Vault product, as well as our newer boundary, thinking about the human access. Then the next layer up is how do I think about networking or connectivity? How do I connect all my different microservices together? I have bare metal and VM applications on premise. I maybe have containers and Lambda functions running in cloud. How do I connect all those things together in a way that they can, A, find each other and communicate, but B, do it in a way that's secure? That's where I'd put console. And then at the very topmost layer, how do we run the applications, right? And so, here I'd put, things like Kubernetes, obviously our version, Nomad, and then Waypoint, which is more of a developer portal experience. So zooming out, these are kind of the layers that we focus on as a company. And I think probably, you recognize a handful of these, but I want to focus in on the middle 2 layers, right? So when we talk about zero trust security, hard to talk about the networking and security separately, right? Because they're so closely related. There's such a high overlap in terms of how security and networking interact with one another. So before we jump into the zero trust side of it, I want to set the stage a little bit as to what's changed. Why are we even talking about zero trust? What's different about security in the cloud versus the way we've always done it? So if we consider the traditional data center, the approach we always took was one of, I'll call it castle and moat. We defended the 4 walls of our data center. We brought all the traffic over the front door, right? Much like a castle, that was our drawbridge. And at that front door, we said, okay, we're going to make it 100% secure, right? And so how did we do that? Well, we had a bunch of networking appliances. We had firewalls, we had web application filters, we had intrusion detection systems. We had all sorts of fun hardware that we threw at the network and said, I'm going to secure the front door. And this way, my mental model, the way I thought about the world was, my attacker is on the outside of my network, so that's bad, right? Public internet is bad. But the inside of my network is good, right? It's high trust, it's secure, it's confidential. We sort of blocked all the threats at the front door. The barbarians are sort of at the gate, right? And so this let us have this nice mental model where we said, okay, the inside, I don't have to worry about a lot of things. If I have a web application and it needs to talk to a database, great, I'll just put the username and password in the source code of my app, right? And I'm sure none of us have ever seen this happen at all. And I think what made this sort of okay is we said, you know what, the application is inside the 4 walls, the database is inside the 4 walls, the source code is inside the 4 walls, so yeah, maybe it shouldn't be in the source code, but it's okay, right? Now along came cloud, and we have these nice fluffy zones, and now we're going to connect everything together into a giant network, right? And so what you start to see is people said, well, why don't I just treat the cloud the same as my data center? I'll just make my cloud 100% secure at the perimeter the same way I did with my data center. What's the difference, right? And I think you very quickly start to realize these are 2 very different things. In your data center, a cable came in through the wall and went right into a firewall. So if you want to go around that firewall, you have to call the networking team and say, do you mind moving a cable around the firewall? At which point they hang up on you, right? If you want to do the same thing in the cloud, you make one API call to Amazon and say, make my S3 bucket public. And Amazon says, 200 okay, it's on the public internet, right? So you start to realize the perimeter doesn't exist in the same way. And in the physical world, there was cables coming through walls. There was a network topology that defined what was the perimeter. And so you had a physical control over it. It wasn't just logical. Where in cloud, it's a logical concept. If your blob store is public, great. If your blob store is private, great, right? Like the only difference is one Boolean, right? And there's no way for Amazon to tell you if it was right or wrong. So I think very quickly you start to accept and say maybe 100% is impractical. Maybe it's 80%, right? And I think, some people argue with me on that number. You might say it's 99.9% because we really understand our IAM controls and our security team is very good and our engineers know what they're doing. Okay, great. Or you might say, on a good day, my engineering team doesn't know what they're doing. So it's 50%, best case. So you can pick any number. I think the key is if you pick a number that's not 100%, your threat model is whatever's left. Even if it's 99.9, it's the 0.01 you care about. And in that 0.01, the attacker is on your network. So all of a sudden, you can see that these had two very different assumptions. In the old world, we said the attacker is on the outside of my network, the inside is trusted. And now you're saying, actually, the attacker is on my network, and my network is not trusted. And these are two very different paradigms. And all of a sudden, it breaks everything about how you thought about security, right? That username and password that before you said, it's okay, right? The attacker's on the outside, everything's on the inside. Now all of a sudden, that doesn't look okay, right? Like, well, doesn't the attacker also see the username and password? Aren't they on the same network as the database? Turns out, yes. Yeah, it's a problem, right? And you see the proof point in this in sort of attack after attack, breach after breach, right? Almost every other week now we see a high-profile breach. I think Uber was literally 3-4 weeks ago, where it's, attacker gets on network and then they're able to move laterally because once you have network access, most of these systems either have static credentials, there's credentials all over the environment, they have default usernames and passwords still set. So you're able to kind of move left to right across that network and get access to a bunch of things you shouldn't. So you start to see the very crux of this. Now, I think in the left-hand side, the way we started thinking about the world was we're going to solve this by having a bunch of IP control, right? We're going to put username and, we're going to put, firewalls in between things and say this IP can talk to that IP address, this subnet can go to this subnet. And so the unit that we managed was an IP, right? We assigned an IP to applications. We managed IPs through firewalls and API gateways and things like that. But all of a sudden, now we're in a cloud world, and you say, okay, well, I have containers over here. They're running in Kubernetes and scaling up and down. I have Lambda functions over here. I don't even know what their IP address is. They come and go all the time. And by the way, I'm going to talk to a bunch of network middleware, NAT, load balancers, VPNs. And so as these applications go over these networks, those IPs are constantly being rewritten, right? By the time I get to my database over here and put a firewall in front of it, what was the IP of that container? I don't know. It's coming and going and auto-scaling. The NAT is rewriting it. The VPN is rewriting it. So the IP address is almost meaningless by the time it gets to the database. So very difficult for me to try and define a control based on an IP. It's too dynamic. It's being rewritten all the time. So how do I rethink about this problem, right? So this kind of gets us to the crux of how we think about zero trust, right? So what does zero trust actually mean? For us, it means two things. One is that I want to be explicit about authentication of any client, so auth-n, and I want to be authentication plus authorization, right? So not only do I need to know it's Armon, I need to know what is Armon allowed to do, right? And if he's not explicitly allowed to do something, then the default policy should be deny, right? It's a default deny approach. So just because you're Armon and just because you're on my corporate network doesn't mean I should have access to a production database, doesn't mean I should have access to decrypt customer data. There has to be a rule that says, yes, I have a business need to do that. It's a requirement for my job or this application or that service to need that level of capability. So how do we make this real? In our mind, it's about a shift to an identity-based control. So rather than an IP-based control, I want to hang it all based on identity. Application A is allowed to talk to application B. Armon, as a developer, is allowed to talk to the production database. I don't care what IP address I'm connecting from. I don't care how I connect to the database. It's about the identity of the service or the person. Now, the problem we have is that at a network level, identity doesn't exist, right? What you see is source IP and port and destination IP and port. That's what exists at a network level, right? There is no identity built in. So the challenge then becomes, okay, how do I actually solve that? And this is where you get into sort of what our view of a 4-pillar strategy for how to actually solve this. The first thing I want to do is establish human identity, right? And this is probably the most well-understood problem. We've been doing this for a very, very long time. This is effectively a single sign-on with some sort of an identity provider. So we might have been doing this on-premise with LDAP or Active Directory for a long time. Now we might be going to cloud and doing it with Okta or Ping or Azure Active Directory or whatever. The key is that I have some definition of who are all my users, what are the groups they belong to, and do I have some kind of cryptographic protocol, whether it's SAML, OIDC, Kerberos, to say, yep, that's Armon, he's a developer, he's part of the HashiCorp organization. Okay, great. If I have that, now I have a way of establishing the human identity and a cryptographic way that I can verify it. Maybe it's SAML or OIDC. Now on the extreme other side of the spectrum is how do I think about machine identity? Or I might put application, you can call this application identity at the same time. I think this is where we actually put Vault. And a lot of people might find this surprising. Most people think about Vault, and the first thing they think about is it's a secret store, right? I use it to put secrets in. And yes, that's an important use case for Vault, but it's actually not the initial problem that we set out to solve. If I go all the way back to the first design document, I think GitHub might call them architectural design documents. Internally, we call them RFCs. We have sort of an RFC process for everything. The very first RFC for Vault actually calls it Kerberos for applications, right? If that doesn't mean anything and you've never worked with Kerberos, congratulations, you live a great life. If you've had the pleasure of working with Kerberos, then the sort of idea behind it was that my applications might have many different forms of identity, right? An application running on top of Active Directory might use AD as the source of its identity as a service account. An application running on Kubernetes might have a JWT token that defines its identity. If I'm running on Amazon, I might have an IAM profile, right? If I'm on Azure, I have a managed service profile, right? So in each of the different platforms I might be operating in, there's some notion of an application identity, but it's managed in a very fragmented way. So it's not easy for me to define a policy in a way that's consistent because my identities are not consistent, right? Unlike human identity, it'd be like running LDAP and Active Directory and Okta and Ping all at the same time in an environment, right? And, thankfully, most people don't do that. So the first problem that we tried to solve with Vault is how do I actually do identity brokering so that I know the identity of the application regardless of where it's running. So that's about deep platform integration into all the clouds, into all the application platforms, into all these different environments. So I can say, great, this is application A, it's on Amazon. This is application B, it's on Google. This is application C, it's running on-prem. Once I know the application and I have its identity, then I can start solving different use cases like secret management, right? So if you've ever used Vault, then when you're defining a policy, it's never tied to an IP. You're never saying, oh, IP address 10.0.0.1, that's a web server, this is what it's allowed to do. Vault never cares about the IP because it doesn't trust the IP. The application has to authenticate itself against Vault, prove its identity that, oh, it's a web server. Great, the policy for the web server says, okay, you have access to these secrets, right? And so kind of level one is, great, we bring in a system like Vault, we remove things like usernames and passwords out of the environment. The application has to actually authenticate against it, get the credentials, and now it can use that to go talk to the database. And so if I happen to be a random attacker on the network, I now have to authenticate against Vault. I have to be authorized to fetch a set of secrets, and hopefully I'm not, right? So that's kind of level one, is how do we actually move those sort of static secrets out of the environment? Level two is really asking ourselves the question, how did that database credential get into Vault to begin with, right? Did I have a human operator create the username and password and then put it into the Vault? Because now they know what that username and password is, right? At the same time, if I have many copies of this web server, I don't want all of them using the same credential, right? If I have 500 web servers using the same username and password to the database, if there's a compromise, if there's a leak, I have multiple problems. One, very hard to understand where was the source of that leak because the credential is being reused all over the place. And two, if I want to rotate that credential, now I have 500 applications all sharing the same credential. So if I change that username and password, I'm going to break all of those at the same time. So starting to say, is there a different model for how we actually do this? And this is where we get into the concept of, what if we actually don't define a static credential, but make it a dynamic credential? So how does that actually work, right? Instead, when the web server comes to Vault and says, give me a database username and password, rather than saving a static credential and then handing that back out, Vault is going to connect to the database and create a new credential. right? So we'll issue a SQL command and say, great, I want to create a new username, X with password Y, and I'm going to grant only capabilities Z to it, right? So I'm going to create a new credential on demand on the fly, and that's what I'm going to give back to the web server. I'm going to say, here, you can use X and Y, and by the way, that's only valid for 24 hours. At the end of those 24 hours, Vault's going to connect back to the database, and it's actually going to delete that user. It's going to say drop user X, right? So we'll delete that username and password. And so this actually moves us to a very different model where instead of having a static credential that we had to manually create and put into the Vault, instead we give Vault effectively super admin, rights, root level credential to the database, and it generates the credential, rotates the credential, and manages the full life cycle for us. So now every one of those web servers can actually have a unique X and Y, and it's time-bounded, and we're rotating it all the time. Why is this important? Well, as we know, application developers do a great job keeping secrets secret, right? The first time the application boots, it gets its credentials, and what does it do? It logs it to Splunk, right? It says, here's my username and password. The moment there's an exception, it generates a traceback, and as part of that traceback, it puts the username and password as an environment variable, right? Or it sends it to Datadog, or it sends it to Splunk, or Sentry, or whatever. So it turns out applications make no effort to actually keep credentials secret. So even if we do a great job bringing the static credentials in and vaulting them, the moment we give it to the web developer, they're going to leak it all over the place, right? And so you see this all the time. If you look at like the Capital One breach from maybe 2 years ago, it ended up that an app wrote the credential into Splunk. 5 years later, someone got access to the Splunk, queried for password. Guess what? The database password was the same 5 years later. And then great, they had access to the database and they were able to pull data out, right? So how do you avoid this, right? One answer is that you write perfect applications. Unlikely, right? The other answer is you make the time window that those credentials are valid very short. Because you assume they're going to leak it to Splunk and someone's going to find it in Splunk eventually. You just want to make sure that 5 years later it's not still valid, right? So that's where this dynamic model really starts to matter, is you move to constantly generating and rotating these. In this case, I picked 24 hours. But it doesn't really matter. That's policy-based, right? You could make it 30 days, a week. We have some customers that go down to 15 minutes with certain certificates, right? So you can kind of pick whatever you want here. The key is that we move to an automated model of generating, rotating, and deleting those credentials rather than a manual once-a-year big rotation type thing, right? So I use the example here of sort of a database because I think it's the most obvious and most common. But this idea of a dynamic secret applies to all sorts of things, right? I'm sure none of us have seen the master SSH key that lets you connect to every machine in production and has never been rotated, right? None of us would have seen that, I think. But I think this list goes on and on, right? Cloud IAM keys, right? Database credentials, messaging queues, right? Certificates, right? I joke, how do you know a certificate has expired? You have a Sev1 outage, right? Because I think for most organizations, they generate a 5-year, 10-year certificate because they don't want to deal with the rotation. They don't want to talk to their security team. That goes into production. Great. 5 years later, turns out the certificate's expired, and now the app goes boom, right? And so the reason I think we do this, we generate these really long, and by the way, that certificate is checked into GitHub. So, great. The private key is very secure. So how do we move away from this? Instead, you want to generate the certificates on demand in a programmatic way, right, based on an API, so you're not checking them into GitHub. The application boots and it gets its credential rather than having it statically saved. And these certificates can then be very short-lived, right? That can be a 1-hour lived certificate. So even if it gets leaked, even if something bad happens, you don't have a certificate that's valid for 5 years or 10 years in an environment. Right? You can have short-lived, constantly rotating. So I won't bore you. You sort of get the point. The idea is anywhere that we have a static API token, a static key, a static username and password, how do we flip that model to instead say, great, actually we can automate that life cycle and not have these things live forever in our environments, right? Because inevitably, the people will put it in Slack or the applications will put it in Splunk, right? So then moving beyond just secret management is how do we think about actual data protection, right? So when we talk about data protection, goes back to this old threat model, right? What were we worried about? Well, over here, if we had a user, let's say they gave us, a credit card number, what did our application do? Well, it would just go and put it in the database. And then we might turn on disk encryption. So we turned on something like transparent disk encrypt. So we said, great, when the database writes the data out to the disk, it's encrypted at rest. Well, what was the threat model? What were we worried about? If we were worried that someone was going to come to our data center, kick down the door, find the hard disk belonging to the database, pull it out, go home, try and load the data and say, oh, shoot, the hard disk is encrypted. Okay, this helped you, right? This was a useful threat model. If they went through all that effort to break into your data center, why they didn't steal your key management device at the same time, and that thing is protected with a 4-digit PIN, I've never understood, but let's ignore that, right? If your threat model is that your attackers on your network, they connect to your database and say select star, the problem with transparent disk encryption is it's also transparent disk decryption, right? So the database will happily read it from the disk, decrypt everything, and send it out over the wire, right? And so, okay, great, every single company that's had a public breach, yeah, they've turned on this disk encryption. How much did that help them? When was the last time you heard about someone breaking into a data center, right? In fact, this is my favorite checkbox in Amazon, is the little encrypt at rest checkbox, right, when you turn on your EBS volume. How the hell would you even find that disk drive? There's like 400 million disk drives in an Amazon region. You'd have to be there all year, and even then you'd never find it, right? So the challenge isn't the physical security of was it encrypted by the time it hit the disk. It was, was it encrypted when it was written to the database, right? And so it's about flipping that model and saying, great, when we get some sort of, let's call it sensitive data from the user, in this case, credit card number, that needs to go to a system like Vault. We actually encrypt it and say, hey, give me an encrypted value, give me a token back. That safe value is ultimately what goes into the database, right? So now even if the attacker gets to the database or they get to the message queue where it's going in transit, what you have is an encrypted value or a tokenized value. It's not actually directly useful, right? You need a second factor breach of your key management system to actually get to whatever the underlying data is. You can't exfiltrate it and take it out with you, right? So really starting to think about data protection and how does that tie in to the application identity. You might say my web service, it's allowed to get the credit card number and encrypt it, but only my billing service is allowed to decrypt the credit card number, right? Maybe the web service has no need to decrypt. And you want to tie that into the identity of the application to say, what is it actually allowed to do, right? So if we zoom back out, now we sort of established these two edges. We know, great, I know my human, it's Armon, he's a developer, he's a member of HashiCorp. I know my applications, this is a web server, that's a database. But how do I actually use those for the internal two flows? Meaning, I have machine to machine or app to app. So my web server wants to talk to my database, right? Or I have human to machine, right? I'm Armon and I need access to the database to debug something. And so I think these are two very different workflows, right? When we talk about machine to machine, you might have thousands of applications and millions of connections at any given time. And so it's very impractical to say I'm going to try and put a device in the middle of all of that, right? What is the middle of this network, right? Very hard to say I can put something, here to intercept all traffic between all of these applications, right? It doesn't work. At the same time, it would create a scalability problem. It would create a single point of failure. So it's not even an architecture that we want, right? So we want something that's going to be massively distributed and decentral in terms of how we do it. And so this really brings us to how we think about console, right? So if we think about the traditional approach, it was application A talks through a firewall. And again, I physically controlled my network, so the firewall sat in between these services. And so great, if A was going to talk to B, I put a firewall and I say IP1 to IP2. Now in a much more distributed and dynamic world, that doesn't work. So we say instead, what if I have a distributed approach? Application A, and I have many copies of it, it's auto-scaling up and down. It registers with console. I have application B. Again, it's also dynamic. And so console is a bird's eye view. It has a catalog of every service, where is it running, what's its current status. And so when A wants to talk to B, it queries in a dynamic way. So it says, great, what's the IP of B? And then I can connect directly. There's nothing in between A and B. I don't need to hard code an IP address or hard code a load balancer. I'm using console to do service discovery in a dynamic way. So I might query for service b.service.console. And then console says, great, you should go talk to IP2. Right? So that's great. It lets me at least have service A discover service B. But how do I restrict which services are allowed to talk to each other? Right? Again, in the old world, I would have put a firewall and an IP level control. But we specifically said I want an identity control. Right? I don't want to manage IPs. I want a rule that says A is allowed to talk to B. The problem is, again, identity doesn't exist in the network. Right? So what I see at the network is source and destination IP. So how do we bring identity to the network? Well, turns out we've been doing this on the public internet for a very long time. Right? We distribute a set of certificates that encode the application's identity. Right? In the same way, when I go to my bank's website, I don't know what the IP address is, right? But I get a certificate back that says, this is Bank of America. Okay, great, I trust the certificate. So A and B shouldn't care what the IP address is. Instead, when A connects to B, it presents a certificate that says, I'm A. B presents a certificate that says, I'm B. And now we're able to establish mutual TLS between each other, right? We have a strong notion of the identity, so we authenticate both sides. And then on the receiving side, we want to do the authorization. Just because you're A doesn't mean you're allowed to talk to me. So I want to check, is there a rule that says A can talk to B? If so, great. That's now my authorization, right? So going back to that explicit authentication done with TLS and the explicit authorization done with a central rule that says which services are allowed to talk to which services, now I allow this to happen sort of end to end, right? So now we're sort of up-leveling and saying, I actually don't care about the middle of my network. The middle of the network could be the public internet. It could be my private data center. It could be A as in Amazon, B as in Google. I don't care anymore because the network is just a bit pipe. Right? As long as the bits get there, I'm not trusting it. I don't assume it's secure. I don't assume it's confidential. Right? So this gets us towards that sort of a zero trust view. Of course, along the way, this would be nice if we could do this with all of our applications, but most of our data center doesn't look like that. Right? We have the joys of legacy. So we have a Java app, great, it wants to talk to a database, let's say. And today we put a firewall in between and say IP1 to IP2. That's what most of our data center looks like. So how do we sort of bring an identity-based approach to our traditional data center where we have firewalls, load balancers, API gateways, hardware devices? The idea is we can actually integrate an infrastructure as code approach with Terraform to up-level this. So I might actually define a Terraform module, right? So using infrastructure as code, and say my input is my set of Java servers and my set of databases, and my output is I'm going to manage, let's say a checkpoint firewall, right? I'm not going to hard code what those set of IPs are because they're dynamic. My application team might deploy a new Java service or move it around or put it in Kubernetes and auto-scale it. And so I don't want to have to, every time I deploy the Java app, I file a ticket, and now someone goes and manually updates my firewall. So instead, when these applications register with console, a new instance can get deployed and register. Console detects there's been a change to a set of Java servers, and we can invoke Terraform and say, hey, there's actually 2 copies of that service now, not just one. And then Terraform can dynamically update this and add IP3 to IP2. So this approach is what we call sort of network infrastructure automation, right? The network infrastructure, like our load balancers, our firewalls, our gateways, most of them have APIs, right? So there's no reason we can't define the behavior in an infrastructure as code way and then connect that to sort of a dynamic source of the application identity, such as console. And that way we can sort of do the networking in an automated way, as opposed to, I think, what we see in a lot of organizations where you file a ticket and wait, days, weeks, months for someone to manually go do this change. But the important thing is now what we've done is at this level, we're managing it in an identity-based way, right? Not an IP-based way. The IP is sort of a detail. It gets filled in on demand. I don't care, is it IP 1, 2, 3, 5, whatever, right? Versus managing a whole bunch of static IPs. The last kind of complexity here is obviously you have a mix of these technologies. I might have my greenfield container applications. They're living up here in sort of service mesh world, right? And then I have my sort of traditional network down here. And so how do they work together, right? And I think you need some way to bridge these two. So this is what we refer to as a terminating gateway. The idea is between, let's say, A and the database, so I might add another rule that says A is allowed to talk to the database. When A tries to reach to the database, it first goes through the terminating gateway. There, it's doing still normal mesh, so we do mutual TLS, we use a set of certificates. The terminating gateway verifies, are you actually allowed to talk to the database? And if so, it terminates the mesh, that's why we call it the terminating gateway. And then it talks to the standard network back. So now I can have a firewall rule here, and these two can work in combination. So now I can mix and match my traditional network, which has traditional firewall and IP-based approach, with a modern identity-based, mesh-based approach, and sort of mix and match these things, right? Because I think that's practically what most large networks look like. It's never going to be all one or all the other, right? So that brings us to the very last pillar, right? Which is, what about my people? I might be a developer, I might be a database admin, right? I'm on the outside of this network, and I need to get access to services on the inside, right? So how do we think about that? Now, I think in a traditional world, we would have said, great, let's take my developer, and I want access to, let's say, a web server that I'm developing. The first thing I'd have to do is jump on, through a VPN bastion. So now I'm on the network, but I have another set of username and password or certificates here. I don't want people to get to everything on my network, so I'm going to have to put a firewall behind the VPN to say, what can you actually get to? So now I have to manage a set of IP controls. Then I shouldn't really give everybody the master SSH key, so I have another PAM tool. So I have to go and get the SSH key to log into the web server. So again, I have more users and groups and more static credentials to manage. And then from there, I connect to my target, right? So this is kind of a clunky workflow. I have multiple systems I have to jump through. As a user, it's not great. But it's even worse as a security administrator, because I have to think about what's the interaction of all three of these systems, right? When you get on my VPN, what can you get to on my network? From my firewall, what set of systems and IPs should you have access to, right? Those IPs are made even more challenging when these applications are dynamic, right? The IPs are changing all the time. And then I need a third layer of privileged access management to manage the credentials of how I get to databases and web servers and other things, right? So it's a lot to manage. So we sort of looked at it and said, is there a way to kind of collapse that and have a sort of more unified approach? And so this actually gets us to the thinking behind boundary. So the idea is I want to have a single layer that combines all three of those. So I run boundary at the edge of my network the same way I would a VPN. And I don't have another username and password. Instead, I connect to the human identity I already have. So I do my single sign-on. I don't need another username and password or another certificate. And then I can define a logical rule that says, oh, my developers, they have access to the web server, right? So unlike a VPN where it dumps me onto the network and now I have network access to everything, when I log in, Boundary is going to say, well, what are you actually authorized for? What should you be able to get to? In this case, I'm only allowed to get to the web server. So I can select that, and Boundary will directly reverse proxy me back. And so now I don't actually need another layer of firewall, because I already have the most restrictive possible thing based on my identity. I might have a different rule, for example. Let's say my database admin. They have access to the database. Oops. So in this case, right, my database admin, they might do the same login. They would be able to connect to the database. If I had to use a firewall rule, though, it doesn't know, am I a developer or am I a database admin? It's going to have to give me access to both of those systems, right, because it can't know which user I am. So in this sense, Boundary can actually be much more tightly restrictive because it knows the identity of the user and what you're actually allowed to get to. So you don't even need to have the firewall in place, right? So now we have we have a different set of challenges, though, which is, okay, well, great. If Boundary is going to connect to the database or the web server for me, how does it actually know what the database credential is or the SSH key is to get to the web server? You're going to find this answer very surprising, that we integrate with systems like Vault. So when we need to get the username and password for the database or for the web server, we can actually fetch it dynamically from Vault and use the ability for Vault to create a dynamic secret just in time. So when we connect to the database, we'll create a username and password, that X and Y, for that one session. And when the user disconnects, we'll delete that. And so the credentials aren't long-lived. They're only used in the context of that one session. The user never needs to see it. And at the end, we clean them up, right? OK, but great. Now the next problem is how do we even know where the database is running? Where's the web server running? You're going to be shocked at the answer, which is that we'll integrate with systems like Console, Kubernetes, Amazon, et cetera, so that you actually use a tag-based or a dynamic-based lookup. So I'm going to query Console and say, hey, what are the IPs of the web servers or those databases, rather than manage it as a static set of credentials. And then, great, the way we want to actually manage this, I don't want to file a ticket and have someone point and click to configure. We want to use a set of rich APIs to manage everything as infrastructure as code. So that way, as I'm provisioning infrastructure, I'm actually provisioning a web server or a database or whatever, I can define the rules as part of that provisioning to say, great, the developer should have access to SSH into that web server they just provisioned. I can define that rule as code at the same time I define the web server and the database and the other pieces, right? So really about sort of a common strategy. So if I pull it back up and we sort of talk about this sort of broader piece here, the way we really think about it is it's all of these different workflows are necessary to get to zero trust, right? I think the assumption of our current network was great. I'm there, I'm high trust, I can access whatever I need. There's not much access control if I go east-west, so my web server can talk to kind of whatever it wants to inside the network. And so we need to kind of get rid of all of those assumptions. I need to have the strong notion of the human identity and the application identity first. Those are the foundations, right? So I start on the outsides as my foundation of I know who's who and I'm authenticating everything that I can touch, basically. And then I'm using those identities either in the machine-to-machine, app-to-app, to restrict and say, OK, you can only talk A to B if there's a rule that says you're allowed to talk A to B. And I don't want to manage the IPs because they're too dynamic, they're coming and going. That's one problem. And then my human-to-machine is the other problem, right? Which is great. I still have users that need to debug things, get to databases, get to web servers, SSH in. I don't want them to have network access. I don't want them on the network. But they still need to have access to things. And to the extent possible, I don't even want them to see the credentials, right? I want to hide that and make them short-lived and dynamic. And that's the other part of this puzzle, right? So all of this sort of comes back to this view and how do we do it in a very different way. I don't think you throw away the perimeter. I still think it's valuable, whether it's 50% or 80%. You should still have a perimeter. You should still have the north-south firewall. But you shouldn't assume that the inside of it is trusted, right? You should start thinking about hardening the inside of the four walls as well. And I think we've seen sort of enough cases of why we should do that, whether it's Uber or Google or Target or pick your favorite, right? And so that's why you can start to see the networking pieces and the security pieces have very high overlap, because the networking model actually defined what our security model was for a very long time, right? And so as we change the networking model, it actually changes the security model as well. So even though you might think they're different categories, they're very close, and I think it touches every application team, because now we're building our applications in a different way, right? We actually have to think about the data security and how we get secrets and how do we sort of access the other systems rather than just say it's the networking team's problem, right? And so that kind of brings us to the sort of like middle two layers. Hopefully that was helpful. I know we're sort of close on time, so I won't talk about the other layers, but hopefully that was a useful session and appreciate you all making the time. Thanks so much.
Right. We have a number of questions. Not much time, but we'll do our best. First things first, people are like not freaking out, but impressed with your setup. Can you share like what you used to deliver the presentation? Like it's an
Sure.
iPad Pro, I guess.
Yeah. It's an iPad Pro, but it would work on any iPad with Apple Pencil. And then the app that I'm using is called Concepts. And the key is that it has sort of an infinite canvas, so you can kind of keep going as much as you want. So this thing is great. I love this app.
Okay. So there are a number of questions around Bolt now, which that was expected, I guess. Let's start with people are like concerned about Bolt becoming your single point of failure, or potentially not single point failure, but a performance bottleneck. Aside from buying HCP, I guess, what would you recommend them to be?
Sure. Yeah. So I draw Vault as sort of a logical sort of single entity. In practice, you would never actually deploy it like this. So I think most of the time when you look at sort of a true production-grade deployment of Vault, you run multiple copies, one in each data center or cloud region that you're in. You're going to have sort of the ability to run multiple copies in each cluster. So if one node goes down, other nodes will automatically take over operation. So you would do a highly available deployment. We can have disaster recovery clusters. You're going to replicate to multiple regions. So I draw it as one thing, but in production and practice, you would never have one single Vault running.
And then again with Vault, they are concerned about there are these ceiling keys at the very beginning when you bootstrap Vault. Are they rotate? They're asking if they are rotated, how often, how does that work? If you can do a quick, it's a big topic, but in a nutshell.
Yeah, sure. So yes, so without getting too in the weeds, Vault has a very deep, what we would call key hierarchy. So any data that you're putting in Vault is encrypted with what is called a data encryption key. The data encryption keys are themselves encrypted with what you would call a key encryption key, right? That is then protected with what you would call a master key. And then that master key, by default, we shard into key shares, right? So if you've ever done a Vault unsealing process, you have many different shares of the key that protect that key. So each one of these keys then supports rotation. So each one of these things can be sort of rotated independently. In practice, the most important one to rotate is this top key, because it's the one that, if you reuse a key too many times, you risk actually losing the value of that key. So Vault can automatically rotate that key periodically so that you always have sort of a fresh data key. The other one that might matter is down here, is the master key, because ultimately maybe too many of these employees leave and they know key shares and you kind of want to rotate that thing. And so all of those different keys can be rotated independent of one another, right? And the topmost keys Vault rotates automatically for you. So yeah, good question. And then if you're protecting this with an HSM or a cloud KMS, you can, it's even another layer.
Exactly. They're asking, I told you, if you are planning to launch an HCP version of Nomad, so a bit out of the presentation, but potential customers here, so.
I would say, we're not announcing anything around that, but I think, very quickly, becoming obvious, a lot of people have a lot of interest in HCP Nomad. So we're trying to figure out what's the right shape of that service. I think some people want just a managed control plane. Some people want the full managed data plane. Other people just want sort of observability features. So if you have any feedback on what you'd like to see from an HCP Nomad, I would love to hear it.
Now you know. And I guess a final one before we try in the audience. And I guess you get that from banks and Fortune 500 and all that. People are concerned about, okay, so you explain all that, but potentially we are now shifting our security we had in our data center by your products, right? So okay, if an attacker got access to HCP, a lot of companies are doomed, right? So how can you calm them a little bit in that regard?
Yeah, no, I mean, that's a good question. So I think even if we're talking about sort of our HCP service, we go through pretty great pains to isolate even internally against ourselves, right? I mean, I think in some sense our biggest threat is not even an outsider. We think about insider threat, right? I think someone who works at HashiCorp is someone I lose more sleep over than an outsider. So the way we design everything internally is strong separation of controls. Our control plane and data planes are segmented. Each of our customers runs in an isolated data plane. And you have sort of multiple different people needed to sort of break glass to get to a customer environment. So the security team and the application team and the infrastructure teams would all need to work together to get to a customer environment. So we take it pretty seriously because I think our biggest risk is actually insider, not outsider.
Yeah, I agree with that. Yeah. And I don't know if there's anyone in the audience willing to ask something because there were more, but we are running out of time. So now's the time to ask Armon. Not sure if he will be back into Barcelona. Okay, no, then it's all right.
Thanks so much.
Thank you.
Cool. Thanks so much.
Really impressive, throwing everything.